Hey guys, and welcome back to class. Alright, today's video we are continuing our unit on electricity and magnetism is all we're up to. Specifically today we're going to look at what's known as transformers and a couple of other things. And the reason why a transformer falls into this section is look at this very first word in the definition I'm giving you. It uses induction. So if you remember, we talked last time about generators and motors, and both generators and motors use induction. Generators transform mechanical energy into, here, let's just do this. Let's do this. ME and electrical energy. So a generator takes mechanical energy. A generator takes mechanical energy and makes electrical, or transforms it to electrical. Geez, I almost said make. Whereas, on the other hand, a motor takes electrical energy and transforms it into mechanical energy. So it's kind of important that you have that down pat. So moving in with this induction, let's just go ahead and take a look at something. A FET from University of Colorado. So a transformer essentially has two coils. You have a primary coil and a secondary coil. And by the way, if you're thinking, this guy really says the word coil strange, remember I'm from Alabama, and so anyway, enough said. You're still watching this though anyway, and I appreciate it. So you've got two coils in this transformer, a primary coil and a secondary coil. And so if you notice, though, there is nothing going on in the secondary coil. The electrons are stationary. The light bulb is not lit. There's no current. There's no potential. But if I grab this primary coil and start to move it, what happens? Well, we get a light bulb and it's starting to light. But what has to take place? Remember, we've talked about induction before. In order to actually have a potential, you've got to have a changing magnetic field. Ooh, I almost want to strike that. You've got to have a changing flux. The flux has to change. And if you remember, flux is what? Flux is equal to, and that's terrible, but it's also my digital pen. There, that's much better. Flux is equal to magnetic field times area. Typically, we change the magnetic field in these problems. Sometimes they'll change area. The AP physics exam used to be notorious for like taking a wire and saying you have an initial area of something, and then somebody pulls the ends of the wire and they decrease the area. Just out of curiosity, what would happen to the potential, to the EMF in this loop if you did that? Well, if you remember, EMF is equal to a change in flux over a change in time. And so if you decrease the area of the loop, you would decrease the potential in the loop as well. So that was a typical old school AP physics question if you were using the numbers in this. So let's go back again to this diagram. You can see that DC electricity, there's really not use of a primary secondary coil with DC electricity because you got to have this induction moving taking place. But look at what happens when we change to alternating current. Now we've got very, very slow alternating current. So let's do something. Let's increase the frequency of this current. Let's increase the frequency. Let's get more oscillations per second. Let's just max it out. And let's increase the amplitude of those oscillations. And now you notice that the light is actually somewhat staying lit. Now again, we have the same phenomena taking place in our house right now, but your lights aren't flickering because of the fact that that oscillation is taking place at 60 times a second. Now notice what happens when I get the one coil inside of the other one. You can see this increased amount of light that's taking place here because it's got to do with how strong the magnetic field is. Now, typical transformers, what they do to strengthen the magnetic field is you put a solid piece of iron inside here. So you've essentially created an electromagnet, which is then inducing a flow of current in the other wire. So what do you think would happen if I decrease the coils in this secondary loop? Let's see if I can do it. All right, it looks like the light's getting dimmer. Let's take it down to like one single loop of wire. And if you notice, the light bulb grows much, much dimmer at this point. So let's also decrease the area of the loop. Let's see if what we got there. So we can change the area of the loop. You should have a little general idea of everything going on at this point in here. So this is how a transformer works. There's two types of transformers. There's step up and there's step down transformers. So the name should kind of be self-explanatory. A step-up transformer increases your voltage, while a step-down transformer decreases your voltage. But remember, this little whole idea, this only works, and it's in the notes, but this is only good for AC electricity is where we use this, because you have to have a changing magnetic field. So the magnetic field, 1 second is going that direction, and then the next second it's going this direction. And that's what causes this changing magnetic field to induce the potential in this other loop over here. Now, what's kind of cool is this. The formula is nothing but a proportion for a transformer. Your first potential over your number of coils equals your second potential. So for example, in this case, you should already know if this is a step up. You should have intuition. You're decreasing the number of coils in this wire. You're decreasing the number of coils. What do you think is going to happen to the potential if you decrease the number of coils? So you should have an idea of how to make a step up or step down transformer. So let's just go ahead and do something. Let's try this formula. This is a very easy problem to do math-wise. Our first voltage is 120 volts. I'm going to write volts AC divided by 30 coils equals, what is your second voltage, your second potential, if you've only got 6 coils on the other side? Notice units, it's a proportion, which means the coils, the word cancels out. Our answer is going to be in volts of AC electricity. And if you take a look, we can do this with our head. 120 divided by 30 is 4. Cross multiply. 4 times 6 is 24 volts of AC electricity. So that is our secondary voltage. So just out of curiosity, what kind of transformer do you call this? Well, that would be a step-down transformer. And this is what's common in all the appliances inside your home. You've got to have something. Your wall outlet in your house is 120 volts. So you've got to have something bring that voltage down before it's used in your other appliances, which is why you'll find transformers. Anytime you've ever plugged the big black box into the wall, that was your transformer. And sometimes you'll have what's known as a rectifier in there too, because it will transform the AC to DC electricity. And again, that's called rectifier. You've probably seen this transformer outside your house up on the power pole. The reason why, there's somewhere in the neighborhood of about 30,000 volts on that line outside your house. And what this transformer is doing is bringing that down to the 120 volts before it comes into your home. So it's making it a little bit safer. If you've ever passed like substations or power stations, these are the huge transformers that you'll see sitting outside them. And they could either be step up or step down based on where they are in the power grid. But typically outside of like a power station, you'll see banks of these. And what they're doing outside of a power plant, they're usually increasing the potential. They're usually increasing it to like 250, 300,000 volts. They're really trying to bring up that potential. And we'll talk about that in a sec. Yeah, this is a short video so far, so we can probably finish this up. What happens is when you get ready to like transport electricity over long distances, having a lot of current actually creates a lot of heat. And the symbol for heat is Q. And so you're actually losing energy through this heat. So what they do is, say for example, this is your power plant over here. What they typically do at the power plant is right outside you'll see a bank of transformers, and they step the voltage way up. So let's say for example 230,000 volts. And what it does is this: you produce less heat in the wire, so you're actually losing less energy that way. And then before it runs to the wires outside your house, you've probably got, most people usually refer to these as like a substation. And somewhere around your house, you'll probably see a bank of transformers, and they'll bring this voltage back down to like this 20,000 volts. And then outside your house, you'll have another step down transformer to bring it in your house. Now, if you're really thinking sharp, you're like, hey, but Mr. Cole, I've got some appliances in my house that they actually call them a 220 volt. Well, on this pole, you've actually got two 120 volts lines. And so you got to think, well, realistically, shouldn't they call that a 240? Well, the reality is this: we're saying 120 volts on these wires. It ranges anywhere from 110 till I've stuck meters in wall, and I've read 140 volts before. So this is really just a general ballpark anyway on what those voltages are. Household circuits. I'm going to see. We don't have much left. Trying to think if we can finish these up. Let's do this. Let's take a little break, and we'll come back, and we'll finish up these notes with one more section. We'll kind of get into this household circuit section. So anyway, later.